We have so far seen tangents to curves. Now next we are going to see something called a normal to a curve at a point. And this is the definition. A line is normal to a curve at a point if it is perpendicular to the curve's tangent there. There means at that point. This new line is also passing through that point that the tangent is passing through, but at the same time it is perpendicular to the tangent, and this line is called the normal to the curve at that point. For example, this is some curve where at this point this is the tangent, then the normal will be perpendicular to that and will pass through that point. Just like you know already that not every curve has tangent at all of its points, there are some curves which have sharp corners where tangent does not exist. So at those points normals also will not exist. Let us next see this example 4, where we are given a curve and a point on the curve at which we have to find the tangent and normal. We already know how to find tangent by first finding dy dx, that will be the slope of the tangent, but then we have to similarly find the normal line also, that means its equation. So we of course start the solution by differentiating both sides of this equation with respect to x, and of course it's implicit differentiation. So by doing that we have first this, where we have applied the sum rule, difference rule, all those things, okay, of derivatives. Now d dx of x squared by the power rule is 2x, and here you have to use the fact that y is a function of x and the product rule for differentiation. So if you keep x as it is and differentiate y with respect to x, you get x times dy dx, minus is already there, and then again this time once more you do the differentiation, but this time you differentiate x and keep y as it is. Differentiating x with respect to x, you get 1. So that's how you get minus y. And in doing this differentiation, you have to use the chain rule because y is a function of x. So here there are two rooms. The outer room is the square room and the inner room is that function y, whatever it is. So first you differentiate the entire thing, the outer room, if you go to that analogy, by the power rule. So that gives you 2y because you have y squared, just like here you got 2x from x squared. Then multiply that with the derivative of the inner room, which is y with respect to x. And this side of course is 0 because 7 is constant. Now from this equation you will be able to find an expression for dy dx, and that expression will be a function of both x and y. So if you do a little algebra here, you can see that on the left hand side you have 2y minus x times dy dx, and if you transfer the remaining things over to the right side, then you get y minus 2x, and then you divide by 2y minus x. Do not worry about the possibility of this 2y minus x being 0. It may be 0, and the points x and y for which it will be 0, their dy dx will not exist. With that understanding, you just find this expression. So that expression I was talking about just now, which gives dy dx, is an expression, it's a function of both x and y. Now from this we are going to calculate the slope of the curve, or the same thing, the slope of the tangent at the given point, which was I think minus 1, 2. So we give the slope a name. You will realize why I am giving it a name. So m is the slope, which is just the value of this derivative when the point is this. That means x is minus 1 and y is 2. So you use this expression and substitute these values, and this is the value that you get as the slope, 4 divided by 5. So that is the slope of the tangent to that given curve, whatever it is. It will be an ellipse. If you go to, for example, Desmos graphing facility online, and there you draw this curve. You write that, you type in the equation, and you will see that the curve is an ellipse like this. In fact, it's given in the text also. So at the point minus 1 comma 2, there will be a tangent, and the slope of that tangent is this. So now that we know the slope of the tangent and also a point through which it passes, we can write its equation. So next we are going to write that. So the tangent at that point is this, where you are looking at the point slope form of the equation of the tangent. Y minus y coordinate of that point through which it passes equals the slope times x minus the x coordinate. I am leaving the task of simplifying this equation to you. You can just do that. And next we are going to find the normal through that same point. So first we find the slope of the normal at that point, which is minus 1 divided by m. Because tangent has slope m and normal is perpendicular to it, so you know already the relationship between the slopes of two lines which are perpendicular to each other. The slope of each one is the negative reciprocal of the slope of the other. So that one was 4 divided by 5, so it will be minus 5 divided by 4. And now we can similarly write the point slope equation of the normal through this point. And it is just to write this that I gave the slope a name, m. And the equation of the normal in the point slope form obviously is this. These two things, y minus 2 and x plus 1, of course won't change because the point is still minus 1 comma 2, but the slope this time is minus 5 divided by 4. So this is the equation, and again you do the simplification. The next topic has a heading. It's not exactly a topic, but it is an observation that you can use implicit differentiation to find derivatives of higher order, and this next example is about that, where you have to find the second derivative of y with respect to x if y and x satisfy this implicit relation, where we will assume that y is a differentiable function of x, actually twice differentiable function of x. Now before we solve this, let me tell you briefly about why the authors suddenly brought in the notion of normal. If you go back to your school optics, you have laws of refraction, you have come across those things, right? Where say you have two media, okay, and light is entering from one medium to another medium. Then it suffers refraction. It bends, the light ray bends more towards the normal, so it is that normal. And such laws are also there for curved surfaces. For example, the surface of a lens. A light ray comes and falls on the lens and then it goes inside, so it suffers refraction there also. So in order to know those angles, angle of incidence, angle of refraction, they are with respect to that normal. So it's trivial to find the normal to a flat surface. It's just the perpendicular. But if the surface is curved, and if it is curved in complicated ways, then finding the normal is really not so trivial, but you can find normal like that. Okay, so that's why. Anyway, let's now go to the solution of this. So we start the solution by differentiating both sides with respect to x first once. Okay, we will go to the second derivative afterwards. Let's see first what we get by doing implicit differentiation just to the equation. So we first have to apply the difference rule, ddx of 2x cubed minus ddx of 3y squared. This side will be 0, you already know, because it's constant, so I have directly written 0. And then by the constant multiple rule, the 2 comes out there and the 3 comes out here from this. And then you apply the power rule here. ddx of x cube is 3x squared. To do this differentiation again, you have to apply the chain rule because it's a composite of two functions. One of them is the function y, which is a function of x, and the other one is the square function. So just like the previous example, here you get 2y dy dx. So this becomes 6x squared minus 6y dy dx, you cancel 6, and then you find that dy dx is x squared divided by y, with the understanding that y is not 0. Alright, now what shall we do? Now we will again do implicit differentiation to this equation, x squared minus y times derivative of y with respect to x equal to 0 once more. So accordingly we do the differentiation, we differentiate this equation with respect to x. And first you apply the difference rule for differentiation, ddx of x squared minus ddx of this product, y times y prime, derivative of y with respect to x. This one is coming from the ordinary power rule, 2x. And to calculate this one, you have to use your product rule for derivatives. You keep this one as it is, say, and you differentiate y with respect to x. So that way you get minus dy dx times dy dx minus. And then you keep y as it is and differentiate this, and that's where you get your second derivative. Now if you bring this term having the second derivative over to this side, but say we write that first, then this is what you get. Y times the second derivative equals 2x minus the square of the first derivative. And here you have to use this thing, that it is x squared divided by y. So we continue the calculation. The next line is y times d squared by dx squared equals 2x minus, here we do that substitution. In place of dy dx, we have x squared divided by y. So we have its square, which becomes x to the power 4 divided by y squared. And then when you finally divide both sides by y, again assuming that y is non-zero, this is what you get as your second derivative, 2x divided by y minus x to the power 4 divided by y cube. So I am ending the video here. We have still one more thing in this section. If you remember that the section also promises to extend the power rule for derivatives to rational powers. Rational powers means we should be able to differentiate, for example, x to the power 3 divided by 4, where the exponent is a rational number. So that is the thing that we will do in the next calculus video. So see you in the next video. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice day.